The headline says, "Scientists have built a synthetic cell from scratch." That sounds like biological magic, but the real story isn't about life, it's about manufacturing. We can easily build the outer shell of a cell, what engineers call the chassis, but we cannot yet engineer the internal microfactories that keep it running, repairing itself, and managing power at the nanoscale. This video reframes synthetic biology not as a miracle of nature discovery, but as one of the hardest engineering problems in history. Building a self-sustaining machine smaller than a virus where every component must survive extreme heat, friction, and chemical stress without external maintenance. The core hurdle is not constructing the cellular chassis, it's integrating self-repairing microfactories that can manage power density and material stability at the nanoscale. When we talk about building these synthetic cells, we are often conflating a complex chemical reaction with a functional machine. There is a massive difference between creating a membrane that looks like a cell and creating an autonomous system that functions reliably over time. Current technology allows us to wrap biological components in a lipid bilayer, essentially building the body of a car without installing an engine or a battery management unit. The result is a fragile prototype that might look alive for hours before it crashes, rather than a working product capable of sustained operation. We are trying to program cells with the same reliability as computer code, turning biological design into a repeatable engineering discipline, but the hardware constraints remain unresolved. Just as AI software is limited by chip power density and thermal throttling in data centers, synthetic biology is currently bottlenecked by our inability to engineer nanoscale energy grids and self-healing materials. The challenge here is not just chemistry, it is hard engineering involving manufacturing constraints and material durability at a scale where standard physical rules break down. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Natural cells have had billions of years of evolution to solve these energy management issues. They are the result of an endless process of debugging, testing edge cases, and refining systems for maximum efficiency in chaotic environments. Synthetic efforts struggle because replicating this intricate internal architecture in a lab setting lacks that evolutionary time. We are trying to write complex code without having spent eons testing for bugs, leading to system crashes in a controlled environment where the slightest deviation causes failure. The physics constraint is real. We cannot yet replicate nature's ability to manage power density and material stability at the nanoscale required for autonomous function. This distinction matters because it shifts the narrative from "we made life" to understanding the hard physical limits we haven't solved yet. For tech-curious viewers, this highlights the physical layer behind biological breakthroughs. It is not a story about discovering new forms of consciousness or magic. It is a story about the difficulty of scaling manufacturing processes down to the molecular level where heat dissipation and material fatigue become critical failure points. We are seeing companies like Ginkgo Bioworks treat synthetic biology as an industrial sector, using automation to scale design and production. However, even with machine learning acceleration driving faster iterations, the bottleneck remains creating biological systems that function with the reliability of silicon chips. The industry is shifting from pure discovery toward manufacturing, yet they are hitting a wall regarding long-term structural integrity and power supply within a microscopic environment. Scaling requires making biology as predictable as computer code, which we simply aren't there for self-repairing systems yet. Without solving the problem of how to keep these internal microfactories powered and stable over time, any synthetic cell built today is just a chemical curiosity rather than an engineered device. We are defining utility by weighing the risks of systems that cannot yet sustain energy flow autonomously or repair their own damage when exposed to external stressors. Leading figures in the field have framed this challenge for decades, not as creating life, but as an engineering problem of intelligent design. The goal is to build machines that can perform specific tasks, like producing drugs or cleaning up pollution, with a level of robustness we expect from industrial hardware. But right now, the gap between what nature achieves and what we can engineer in a lab is defined by our inability to manage power density at the nanoscale. We have built the chassis, but the engine that drives it requires materials and energy systems that do not yet exist in our manufacturing capabilities. This reframing helps viewers evaluate future claims about biomanufacturing, synthetic drugs, or lab-grown materials with a critical eye toward engineering feasibility rather than biological wonder. When you hear about a new synthetic cell, ask yourself, does this system have the internal infrastructure to survive on its own? Is there a solution for how it manages heat and power over time? Or is it just a collection of chemicals that look like a cell until they degrade under stress? The answer determines whether we are witnessing a breakthrough in engineering or simply another variation of complex chemistry. The current state of the art shows us that while constructing a cellular chassis is relatively straightforward, integrating self-repairing microfactories remains an unsolved problem requiring deep advances in materials science and energy management. We are not failing at biology, we are hitting the hard limits of nanoscale manufacturing. The path forward requires treating these biological systems as hardware first and chemistry second, focusing on durability, power efficiency, and repairability just like any other complex machine. Until we solve the physics constraints that prevent autonomous operation at this scale, synthetic cells will remain prototypes rather than products. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.